Okay, hello everyone. I hope you all had a good weekend, and um, thank you for coming to the guest lecture on Wednesday if you were there. There's a decent amount of people, so that makes me happy. Um, if you weren't there, the lecture is posted in our Google Drive. Okay, so also I wanted to add that for those of you that have been having a hard time following my lecture, there's now a YouTube channel. I think I sent it in SIGA. And so the benefit of that is that you can add subtitles if you need. So yeah, that's about it. Also, thank you all for submitting your assignments on, I think it was Friday. So I'll get those back to you in the before Friday, hopefully. It's a lot less marking for me if most people submitted in pairs, so that's nice. Is there any questions before we begin on your referee report, maybe, which is due on June 5th, I think? I changed the date back a few days so that you guys would have extra time. But if there's any questions now before we start, let me know. Okay, so if not, let's start. The game plan for today is that I'm kind of behind because I'm supposed to be restarting regression discontinuity, but we had the guest lecture, so I won't be able to start quite today. Hopefully on Wednesday we'll get there. So today we're going to talk about synthetic controls and then read a couple papers. So Nicholas asked, quoting other papers related to the referee paper is okay. Yeah, so I mean, obviously the bulk of your paper should be about the paper that you're talking about, but you can also use other papers maybe to talk about um, external validity or internal validity or other issues, especially maybe the context or how it's relevant. So if you're doing like a bit of a literature review in your context section, that would definitely be fine. So yeah. Okay, let's go ahead and start with chapter 5 then, hopefully finish. Share screen. Oops. Oh man, everyone's coming. I don't know why I put you guys in waiting rooms. I don't know how to change it. So, sorry. Okay. Nope, not R. Nope, not Theta. Okay, so where are we? Yeah, way back. Okay, so just so you guys know, I have event study designs in the notes, but we're kind of running out of time, so I don't think I'm going to cover them. So we're gonna instead focus on synthetic controls because I think it's more interesting and definitely easier to implement for you guys. So it could be useful for some of your thesis, whereas event study designs are pretty tricky to implement. So I'd rather concentrate on synthetic designs, but I will give you the general idea of one in case you do have it in mind for a future project. So basically, we already talked about difference in differences. And remember how in a difference in difference, we have two time periods, before and after treatment, right? And typically we have two groups as well, those that are treated and those that are in a control group, so not treated. So it's a very clear setup. You have two time periods and two groups. Very clear cut case. Well, an event study design is more of a generalization of a difference in differences where you can have different units treated at different times. So, for example, let's say we want to look at the effect of job loss, so becoming unemployed on earnings. Okay, so if we're looking at losing your job, on your earning outcome. So this will be at the individual level. So let YIT be earnings of individual Y on time T. Okay, so basically the setup, I'm not going to concentrate too much on it because I don't expect you guys to replicate this, but the big point is that each individual who is treated, you're treated if you lose your job, but not everyone is going to lose their job at the exact same time. So people will lose their jobs in different moments of time. So we need to create a dummy variable for each individual at the point that they lose their job. So every individual will have the same difference in differences set up, except for the fact that they just have a different point of time in which they're treated. But we want to set K as the period in which they're displaced, so that everyone loses their job at K equals 0. Okay, so that's what you want to rescale to. So you set, basically you want to rescale everyone so that they lose their job at 0, and then you can look within maybe a 4-year period before and a 4-year period after to examine the effect. But there's not going to be the same 4-year period for everyone, right? So if I lose my job in 2013 and someone else loses their job in 2015, to be able to compare them, we need to say we both lose our job at K equals 0 and then compare the outcomes before and after. So obviously with that, since you're using different time periods, it's important to include time fixed effects because there are going to be differences over time. Okay, so this would be the graph of what it looks like for an event study design. So with trends, without trends. Okay, so 0. They're saying, wait, what is this? Per quarter. So this is earnings, and this is years since displacement. So you can see, even though people might have, there's a bug, even though everyone might have lost their job at different times, we have years since displacement is 0. So that's the period where everyone receives treatment. So we're rescaling everyone to this time period. And then we can compare the treatment group to the control group. Okay, so we're saying 0 is the difference in income. This is difference in income, right? So this is the control group basically. So you can see they were earning lower before the control group, even before they received the treatment effect, and then you can see a large decrease. Okay, so it does have the same principles as difference in differences. The main difference is that you can have multiple groups treated at different times. So that's more flexible because say that maybe you have this program that's nationwide, but it's implemented in different stages. So maybe only 10 distritos receive this program at the beginning, and then it rolls out to another 10, and so on and so on. But we want to examine the effect for all of these groups, right? Because we care about the effect on average, not just for 10 groups at a time. So we can actually analyze that by using the same difference in difference principle, but just rescaling so that they all are treated at a period, like K equals 0, and then looking at a period of time around that treatment that's equal for all groups. And the good thing is that if you think about the first group that receives treatment, they have a really large control group, right? Because no one else has received treatment yet. So you can think of groups that are going to receive treatment but haven't yet as a control group, right? But then once the second group receives treatment, the control group becomes smaller and smaller because more districts have subsequently become treated. So that's kind of the trade-off, is that it may be more flexible, but you're also losing comparison groups over time, so it might not be as balanced. So that's really all I wanted to mention about event studies. I think we're going to focus on synthetic controls instead for this semester, just because of the time constraint. We only have 11 weeks this term. Okay, that's what I said. I'm not going to worry about these examples, but just to give you guys an idea. So say this is your treatment status. So we look at this little matrix. This has I equals 1 or 2. So I equals 1 is the treatment group, and I equals 2 is the control group. And then we have different time periods. So t equals 0, t equals 1, 2, and 3. Okay, so you can see that in the treatment group, their treatment status is always 1. Okay. Well, okay, so this is dt. So t is the treatment time period, t minus 1 and t plus 1. Okay, so they're treated in period t equals 1. Oh, wait. In period t, I guess. Okay, so they're the treatment group, and you can see the control group. They're not treated in that period, right? At period t equals t, the control group is not treated, so they're a valid control group. That's basically a traditional way of using a difference in differences. This case is not identified because you can see in the period that group 1 is treated, in period t equals t, the control group is also treated in that period, right? So if they're treated in the same period, we don't have a control group, right? Because you need an absence of treatment for at least one group. So this is not identified, it's not valid. But to have validity in an event study, you can have it that the second group, the control group, receives treatment, except in a period after. Okay, so you can see here that while, oh, this is equals to actually, while the treatment group receives treatment in this period, I guess t is equal to 2, the control group doesn't receive treatment in that period, right? So they're the control group in that period, but they receive treatment in the subsequent period, in period t equals 3. So they can act as a valid counterfactual group and later receive treatment, right? So that's possible. And so that's really the benefit of an event study design. When you have your data such that there's kind of gradual treatment effects across an area, you definitely should consider using this just to be able to use as much data as possible. Okay, that's really all I'm going to say about event study designs. If you're more interested in using it for your own research, you can send me an email and I'll try and send references for you guys. If not, we're going to look at synthetic control methods now. Okay, okay, so how many of you guys have heard of a synthetic control method before in another class? Anyone? No one has heard of a synthetic control method or used it in another class? Nope. Wow, not that I remember. Oh, we're covering new territory. That's great. Okay, so I love synthetic control method. It's really great when you have a difference in difference kind of setup. So you have some sort of policy change that affects a group, except it's really hard to actually use difference in differences as a methodology because maybe your common trends assumption fails. So when you try this, and if you can't come to a causal estimate using difference in differences, I definitely recommend turning to synthetic control method because it's basically creating a set of synthetic controls across a whole group of or districts or whatever untreated units that don't receive treatment, except we're not using the whole group, we're only weighting certain characteristics about each group so that we can create the most accurate counterfactual to our treatment group as possible, right? So it's not a real control unit that we're looking at, it's basically a combination of a bunch of different groups to most accurately represent the treatment group. So This way it's really good at finding causality more so than difference in differences. So that's what we're going to talk about now. And I won't get to it today, but for Wednesday at the beginning of class, I'll show you guys some code on how to run it in Stata, so you guys can have a good idea of how to use that in case you were thinking about doing it for a thesis. Okay. So yeah, synthetic control methods, or SCM, have become widely applied in empirical research in economics, and other disciplines. So the validity of SCM estimators depend on important practical requirements, right? So basically, remember when we're looking at a good control group, we always want the balance of characteristics pre-treatment, right? So we can create our synthetic control on the basis of looking as close as possible to the basically treated group before treatment. That's our goal, okay? So ignoring the context of empirical investigation and the characteristics of the data might miss the mark, producing misleading estimates. So yeah, a lot of times when you're doing a difference in differences, or when economists have used difference in difference methodologies in the past, they tend to just use a random state or the closest one, assuming that it should be valid. But oftentimes, there's so much heterogeneity between states or districts that it's really hard to compare to just because they're neighboring. They can have completely different economies or cultures or whatever factors. So basically this is to provide a better counterfactual than what a difference in differences can provide. Okay. So their goal really is to make it more, to create a control group more relevant to data requirements rather than just saying, oh, well, this should be good because it's neighboring to our treated unit. No, they really wanted to make it more empirical based and more testable as well. Okay. So yeah, we were just talking about difference in differences, so this should be fresh in your mind. Often they're used to evaluate the effects of events or interventions that are affecting aggregate units. So whether it be a state, a school district, a country, county, something like that, even city, metropolitan area. Okay, so this would be an example of a comparative case study. So basically a comparison group is selected to evaluate an instance or case of an event or policy of interest, right? So we have our treated group and we're choosing a control group to be our comparison. Sorry, I can't speak today. Okay, so one example, I don't think we're going to be talking about this, but I mean, it's a good paper. You guys should read it. It's a very classic difference in difference paper. So Card 1990 looked at the effect of the Mariel boat lift, which is a large and sudden influx of immigrants to Miami, and looked at that effect on labor market outcomes of Native workers in Miami. Okay, so you can see how there's this sudden unexpected shock, and then he looks at the outcome of the treated area to some non-treated areas. So using the difference in difference design, he combines 4 other cities in the south of the US, so Atlanta, LA, Houston, and Tampa. And so he uses those 4 to approximate the change in native unemployment rates that would have been observed in Miami if they hadn't received treatment, so in the absence of the Mariel boat lift. But he doesn't really use a synthetic control design because he's not trying to combine these places in such a way that they look identical to Miami before. So really what a synthetic control is trying to do is create a weighted average of these untreated units to basically produce identical characteristics of the treated unit before intervention. Okay, so why do we not want to consider post-treatment characteristics when we're creating a synthetic control group. What would you guys think would be the problem if we said for the whole time period, let's make our control group look as similar to our treatment group as possible for the whole time period? What would be the problem with that?
Sorry, could you repeat, please?
Yeah. So if we're creating a synthetic control group, we're making it, basically we create a bunch of different control units. So say we're looking at states, we have one treated state and maybe 40 other control states. So we want to create a synthetic control of these 40 states by combining characteristics or weighting characteristics of each state so that our control that we create, the synthetic control, looks as similar as possible to our treatment group. But what would be the problem then if instead of just looking at the pre-treatment period, we tried to make our synthetic control as similar as possible to our treatment group, but for the whole time period, so before and after treatment? Where would that go wrong?
You could lose the benefits of having variance, like to identify the impact.
Yeah, so absolutely, you would not be able to identify the true impact because remember the post-treatment period is where we measure our treatment effect. So if we're making our synthetic control group look similar to our treatment group in the post period, we're just removing all true treatment effect that there is. So we wouldn't actually estimate an effect if it was there. So that's why it's important that we only look within our pre-treatment characteristics. So that's exactly correct. Okay. So the main idea is that we're combining untreated units, similar to the work of Card in 1990. And that's just to provide a better comparison to the treatment unit than any one untreated unit alone. So we're saying instead of combining Miami to just Los Angeles, maybe they're not so similar. It would be better off to create a fake Miami using the characteristics of 40 other cities instead of just one city, right? So that's the justification. It's kind of similar to matching, I guess, in that way. Like you're trying to find as similar as possible, but we're actually creating a synthetic control, which means it doesn't exist. It's some combination of other untreated units. Okay, so it's become more popular in the last year. Here's some examples. So they look at it, the right to carry, like gun laws, legalized prostitution, immigration policy, corporate political connections, some taxation, some organized crime, more immigration, minimum wages. That's just all one. So yeah, there's a lot of new papers on this, so you guys can check them out if you're more interested in a synthetic control strategy. We're going to talk about a paper hopefully later today on a smoking policy change in California. Okay, oh, here we go. Okay, so the typical setup of a synthetic control is that we'll have one aggregate unit, such as a state or school district or whatever unit, normally it's at a macro level, so like I said, a state. They're going to be exposed or receive some sort of intervention or policy, okay? And so they receive a policy and they have a pre-treatment and post-treatment. And from that one state, we'll create a synthetic control of a bunch of other states. And then we can look at their pre and post period. So the pre period should be identical as possible. And then based on that, we'll say that, well, since their pre period characteristics are identical, we'd say that the post period trend in our outcome for our control group will be basically what the treatment group would have observed in the absence of policy, right? That's our ultimate goal, is to create a valid counterfactual, which is what the treatment group would have observed in the absence of treatment, which we actually can't observe, or else we wouldn't have this whole problem of the counterfactual and this class wouldn't exist. So yeah, this is the whole point of basically, well, impact evaluation strategies. So yeah, one example is Abadi et al. 2010, which looks at the effect of a large tobacco control program in California in 1988. So we're going to read that paper later. So traditional regression analysis techniques require large samples and many observed instances of the event or intervention of interest. So they're often ill-suited to estimate the effects of infrequent events such as policy interventions on aggregate units. So that's just talking about a traditional OLS. Obviously, a difference in differences would be better, but we said that can have some problems as well, especially if it doesn't match our, or if it doesn't meet our identifying assumption, which is common trends. Okay. Sorry, I missed an F. So economists have approached the estimation of the effects of large-scale but infrequent interventions using time series analysis and comparative case studies, right? So that's the difference in differences that I just mentioned. Single unit time series analysis can be an effective tool to study the short-term effects of policy interventions, right? That's just in the cases where we expect short-term effects and they have to be of large magnitude. Normally though, the use of time series techniques to estimate medium and long-term effects is complicated because we obviously have shocks over time. So it's hard to estimate for just a one single unit. This is looking at basically say, okay, well, we're only going to include California. We'll do before and after and just include fixed effects. Well, that's probably not good enough because there's different shocks that occur over time and maybe other factors change. So a difference in difference would definitely be better than that. But the drawback is that selection of comparison units has not really been formalized and often relies on informal statements of affinity. So when they say affinity, they just mean connection, like how related the treatment and control group are. So, right, so what they're saying is, or what I'm trying to say is that so far when we've talked about a difference in differences, you look at a lot of papers and they just seem to randomly choose a control group on the basis of, oh, well, it's nearby, or they seem to be related. But when we're doing empirical analysis, our choices should be based on data. It shouldn't be based on anything else like feelings or, well, they're close by. So you actually should have data to back up why you're choosing your control group and whether it's the best one, right? So in a classic difference in difference setup, it really hasn't been clear theoretically how you should choose the control group, right? Of course, we know that, okay, well, the control group has to match common trends and they should look similar and blah, 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 but on how to choose it really isn't as clear. So when you can apply a synthetic control method, it's very simple because you actually can just use all the data you have on all the states or units that you have and try and find the optimal comparison group based on the combination of characteristics that reflect the true characteristics of the treatment group. So it's definitely nice because it's a lot more precise than choosing a control and a difference in differences. Okay. So yeah, the problem with difference in difference mainly is that when the unit of observations are small number of aggregate entities, so it's a country or region, it's really hard to find one single unit that could provide a good comparison for the unit affected by the intervention. So I'm sure a lot of you have tried to do difference in differences for your thesis paper, and I'm sure you've struggled with the common trends. And that's just because there's so much heterogeneity between states or districts or whatever two units that it really is hard to find two that look identical where one receives treatment and one doesn't. So that would be the biggest challenge of difference in differences. And the nice thing is that synthetic control offers a reasonable solution to that. Okay. So the synthetic control method is then based on the idea that when units of observations are a small number of aggregate entities, so groups, just like states, districts, normally not countries because we don't like to compare cross countries because there's so much difference, but some sort of aggregate entity, a combination of the unaffected units will often provide a more appropriate comparison than any single unaffected unit alone. So that's the true benefit of a synthetic control method. And so the synthetic control seeks to formalize the selection of the comparison units using a data-driven process, right? So the main drawback of the difference in differences is that there's really no formal way to choose what group you're going to have as your control. People just tend to say, oh, well, the closest state, they should have similar economic shocks. Well, that might not be true because maybe they have different industries, maybe they have different types of labor market, education levels, all these different things that could really affect the common trends assumption. Okay. Okay, any questions on the motivation for synthetic control before we go into a bit of the setup? Okay, great. Tell me if I'm talking too fast as well. I know I can tell I'm talking quickly, so yeah, just let me know. Okay, so here's the setup for the synthetic control. So we're gonna have data for j plus 1 units. So j equals 1 through j plus 1. So without loss of generality, let's assume that the first, wow, I really can't spell. You guys don't come to me for English grammar because I'm the worst at it, clearly. So assume that the first unit, j equals 1, is the treated unit. So j equals 1 is always going to be the treated unit just for simplicity. So we're going to call the donor pool the set of potential comparisons. So j equals 2 to j plus 1. So these are all the untreated units not affected by the intervention. So we have j equals 1, treatment. The rest, j equals 2 to j equals j plus 1, that's our set of control groups that we could potentially use as the control. So far, they're just untreated units, and we haven't done anything with them yet. So we're going to observe t time periods, and the first period, t0, wait, what's the first t0 period before? Okay, so yeah, the first t0 periods before intervention. Okay. So for each unit, j, and time t, so we have a group, aggregate group j, and time t, we observe the outcome of interest, so yjt. Okay, so, and then for each unit j, we also observe a set of k predictors of the outcome. So that's going to be our set of x's. They're basically characteristics. So when you think of all the balance tables we've done, you can think of those as part of your x's, right? They're just descriptive characteristics, whether it be income, education, whatever things affect the outcome variable. It will obviously be slightly different depending on what outcome is. So that'll be a set of x's, capital X for ij to, or sorry, 1j to x kj. Right, so it's 1 to k characteristics for individual j. And so that could include pre-intervention values of yjt, so your outcome. That's really good to include, right? So whenever you have data on your outcome variable pre-treatment, it's always great to include that, whether it be for randomization, we wanted to put it in our balance table, right? For difference in difference, we use our outcome pre-treatment to check common trends. For synthetic controls, again, we're going to want to use our pre-treatment outcome variable to help predict our outcome now, right? So If I had high income in period T-5, you would assume that would predict my income in this period, right? So your pre-treatment outcome is probably the best predictor of your outcome now. That's why we always want to include pre-treatment outcomes when we have it in our analysis. Okay. Still following along? Okay. So for each unit J, so whatever group and time period T, we're going to have a outcome YJT for the end. So what's that? I don't know, like, sorry, I can't speak. So YN, and that will be the potential response without intervention. So that's the outcome for the groups without intervention, okay? And then for the unit affected by the intervention for our treatment group, so J equals 1, right? J equals 1 is always our treated group. And a post-intervention period, so that's actually T is greater than T0, right? So after T0 is the post-treatment, sorry about that. We define Y to the I, or 1T, to be the potential response under the intervention. So this is your, basically, this is your Y1I. Remember when we talked about our two potential outcomes, the outcome when you receive treatment and the outcome when you don't. That's basically what we're saying. We just have slightly different notation. So this is the outcome when you do not receive treatment. So this is among all the J that are not treated. And then this is among J equals 1. So that's the unit that is treated. So it's the same thing as your two potential outcomes that we've talked about so many times before. It's the exact same, just slightly different notation. Keep you guys thinking. It wasn't intentional. Then the effect of the intervention of interest for the affected unit in period T with T greater than T0 is then, so your treatment effect for unit 1, right? That's the treated unit, is the difference between those two average outcomes. So it's just the difference in means. So because unit 1 is exposed to the treatment after period T0, it follows that for T greater than T0, we have Y1T is equal to Y to the I1T. So that's just saying that for our only treated group, they experience the potential outcome that you have received treatment. So that's really logical. And then for the unit affected by the intervention and a post-intervention period, we observe the potential outcome under the intervention. Oh, that's just what I said above. So these two are the exact same thing, but one's numeric and one's in words. Just that the treated unit is going to receive an outcome of which you receive treatment after the treatment period. It's really convoluted. Okay, so the policy evaluation challenge is to estimate this YN 1T, right? So for T greater than T0. So this is how the, oh, I have to chat. So we use X's to predict YN, correct. We'll get to that, how we choose our X's and how much weight we give to each X's in a second, but yes, to predict YN, we're using the X's, the set of characteristics. Good question. Okay, so to estimate this YN, which was the basically outcome of not receiving treatment for the post-treatment period, we need to see how the outcome of interest would have evolved for the treatment unit in the absence of the intervention. What is this called? What do we have a name for this? Starts with a C. Counterfactual, yes. Nice, Susanna. That's correct. It's the counterfactual, the outcome of interest for the treatment group if they had not received treatment. So we don't actually observe that. So we need to provide an estimate for it. That's the whole goal. So yeah, it says right here. This is the counterfactual outcome as the affected unit was, by definition, exposed to the intervention of interest after t equals t0. So we can't use the treatment group to find the counterfactual because they're treated. So we need to find some sort of control group to estimate the counterfactual. Okay. So yeah, just a note, I don't know how important this is, but obviously we're going to have panel data or some sort of time series so that the effect of the intervention can change over time. So you can see a large treatment effect at the immediate period and it can maybe decrease in the long term or whatever, however it be. It is what it is. Okay. So the estimation is that we're trying to reproduce this yn, which is the counterfactual, right? So the outcome for the treated group if they hadn't received treatment. And we're going to use a small number or large of unaffected units, so units that have not received treatment, but have similar characteristics to the affected unit at the time of the intervention. Okay. So as we talked about, which is basically the motivation for using a synthetic control over a difference in differences, is that it's often difficult to find one single unit that didn't receive treatment that provides a suitable comparison for the unit of interest. So if it was really easy to find a suitable control group, then I would say go do a difference in difference, because if you can satisfy the common trends assumption, don't waste your time making a synthetic control. But often that's really hard to do, just as finding a perfectly valid instrument variable is hard to do. So this is a nice kind of secondary option to a difference in differences that allows you to create an optimal control group, right? So we basically want to create a combination of units in the donor pool that can approximate the characteristics of the affected unit much better than any one unaffected unit alone. So if we can do this, we should definitely opt for synthetic control over a difference in differences. Right, so synthetic control is going to be the weighted average of the units in the donor pool to estimate the characteristics of the treatment group. So the synthetic control can be represented by a j times 1 vector of weight, right? So we're going to have weights equals W2 to WJ equals 1. Remember that the first unit, so j equals 1. Oh, wait, that should be j plus 1. That should be 2 to j plus 1, because j equals 1 is our treatment group. Sorry, that's a mistake in my notes. Okay, so given W, the synthetic control estimator of this yn, which is our outcome for the non-treated units, or basically what the treated group would observe if it hadn't received the treatment, and the treatment effect, tau 1t, is this. Okay, so we're going to estimate this yn. So y hat n is going to be a summation for j equals 2 to j plus 1. So those are maybe like all the other states or provinces. And so we're going to have a weight multiplied by this w. Oh, why do I keep saying w? Y, jt. Okay, so we're weighting the outcomes by state. And then we can take the treatment effect as just the difference in means between our treatment group minus our synthetic control group. So expressing the comparison units as a synthetic control motivates the question of how the weights, Wj, should be chosen in practice. Okay, so we're estimating this yn using a set of weights based on the j units of their y. So whatever their outcome is, we're weighting them. And how do we choose the weights? Well, okay, well, just to be clear, this is the post period. So we're looking at the treatment effect. So this is after treatment is received. So this is really what the counterfactual is. And so we estimate it using a bunch of different groups. So j equals 2 to j plus 1. And so this is their outcome, but we're weighting each outcome. So instead of just comparing one j, so say j equals 2, we only use that, and we use a difference in difference. Then if we do that, we would do y like 1t minus y 2t. So our treatment group is 1 and our control group is 2. So we're just comparing the mean outcomes between the treatment group and control group. But if we don't have balanced characteristics, then we're going to use synthetic control method. So we have a bunch of different states or units of untreated groups. And so we need to choose an appropriate weight for them that they basically create a valid counterfactual. Is that clear? Did I lose some people with my explanation?
I don't understand why the estimated y is actually an estimator. It's not like a new kind of observation.
Right, okay, so you mean this y hat?
Yes.
Okay, well, so what we do is we have all of these yjt's, they are observed. So say we have 50 states. So this is the y that we observe for a treated unit. And these are all the y's that we observe for the untreated unit. So whatever groups do not receive treatment. But we have multiple of them, so we want to take the average, right? Or maybe we want to weight them in different ways. So maybe we don't want to just take the average. We'll weight them based on how closely they are related to our treatment group. So that's why we produce this y hat for the control group, because this isn't observed. It's some combination of all of the untreated units of their outcome. So we don't actually observe this. We only observe these y's and this y for the treated group. So this y hat does need to be estimated. Does that clear it up?
Yes, thank you.
No problem. Okay. So ideally, we want to choose these weights so that the resulting synthetic control best replicates or resembles or just looks identical to the pre-intervention values of the treated unit of the predictors of the outcome variable. So we're going to use basically predictive variables of the outcome and make them look as similar as possible between the treated group and our synthetic control. And so whatever weights can achieve this are the ones we will use on our outcome, on our y. So the vector w is chosen to minimize this, so the absolute value x1 minus x0 w. So x1 would be the characteristics of the treatment group, and x0 would be the characteristics of the control unit with a w weight. So we want to minimize the difference between those two. So when we minimize the distance between those two, we're making them look as similar as possible, right? So that's really the goal of how we choose our weights for synthetic control. Oh wow, time's really flying by. Okay, so let's take our 10-minute break here, and we'll come back at 7:04 and finish synthetic controls, hopefully. Okay, any questions before we take our break? Okay, great. I'll see you guys in 10 minutes. Okay, let's start again. I see only half of you made it through the 10-minute break. Great. Okay, so is there any questions on how we would actually set up a synthetic control? Okay, so why would we actually use a synthetic control? Well, it makes really transparent the discrepancy between the treated unit and the combination of untreated units that provide the counterfactual of interest. So it's really transparent. We can look at the data and verify, whereas with a difference in difference, when we just choose one unit as the control group, there's a lot of subjectivity there and a lot of room for choice. So it's not as objective. And the goal with empirical analysis is always to be as transparent and data driven as possible. So that's definitely a benefit of the synthetic control. It also makes really clear the extent to which the observations in the donor, oh, sorry, yeah, I'm going to repeat how to calculate the weights in 1 second. Okay, so it makes clear the extent to which the observations in the donor pool can approximate the characteristics of the treated unit. So I'm going to go back and explain the weights. So, oh, okay, so the weights are chosen based on the minimization of this equation. So what we want to do is we want to set up characteristics that describe our outcome variable. So say our outcome variable is test scores for students in a school. So what would affect test scores in our outcome variable? Well, probably test scores before treatment is a good indicator. So we should include that. Maybe school quality, maybe highest degree of teachers, family income, a bunch of different characteristics that would affect your outcome variable. So we have a long list of these characteristics that we think describe our outcome variable. And then what we want to do is minimize the average characteristic in the treatment group minus the average characteristic in the control group, given some weight. Okay, so what we do is we want to make them look as similar as possible. When you're doing this in practice, so if you're using Stata, for example, the command is really simple. I was going to show you it on Wednesday because I'm not quite prepared to share my code yet. I just want to make sure it runs well first. But it's very simple because the command is actually just synth. I'll write it in the chat. Synth. I think you need to go SOC install first. And just do synth and then follow the command code. And you basically need to put in all of your predictor variables that will help define your X variable. And you need to define when pre-treatment period is. And then using that command, it will automatically weight your variables to match as closely as possible to the treatment period. Okay, so I'll show you guys some examples first thing on Wednesday, and that should clear it up a lot. But yeah, we're just choosing the weights for each control unit. That's the main analysis of the synthetic control, so that when we combine these weights, our synthetic control looks as similar as possible to our treatment group. And so it's just minimizing the difference between the pre-treatment characteristics of X for the pre-treatment characteristics for our treatment group minus those of our control group given some weight. So some weight will be attached to each characteristic for each different group. So that's the whole procedure. It's pretty straightforward and it's really easy using Stata. So I'll show that on Wednesday. So if you're thinking of doing it for your thesis, definitely come and see how you can code it. No problem. Okay. So sometimes with the synthetic control, it might not always be possible to approximate the characteristics of the treated unit using a weighted average of the units in the donor pool. In that case, it would not be appropriate to use synthetic control, because the whole purpose of synthetic control is that we can approximate a good counterfactual using a bunch of different control groups. But if we can't get the pre-treatment characteristics to match well, then we likely don't have a good counterfactual, and so it's not valid. That being said, that's really unlikely unless you have your treatment group is a huge outlier. So if it's really different than all other groups, then it's an outlier, then it's unlikely that you can find a good comparison group anyways, so difference in differences wouldn't be good either in that case. So normally, if you have challenges of finding a good control group for a difference in differences, a synthetic control can usually offer a good comparison. Okay. So some potential problems that synthetic control doesn't solve is that, yeah, as I said earlier, sometimes a group of controls can't make a valid counterfactual no matter how you weight them. And that would occur if your treatment group is an outlier. I'm sorry, getting really loud in my household. Okay. It also can't address spillover effects. So if the units affected by I just missed all my Fs. If the units affected by spillover effects are included in the synthetic control, the researcher should be aware of the potential direction of the bias. Okay, so right, if you have control groups that are somehow affected by the treatment of the treated group, that would still create bias, right? Because, like, what is the problem of spillovers? It's that our control group is now receiving some sort of treatment effect, so they're probably not offering a good counterfactual of the treatment group in the absence of treatment, right? The whole point of having a counterfactual is to estimate the outcome of the treatment group in the absence of treatment. Sorry, 1 second. I need to yell at my family. Sorry, 1 second. Sorry, my family is playing TV. I don't know if you can hear it, but it's distracting to me, so. Okay. So the spillover effects, yeah, like I said, if the control group is affected at all by the treatment of the treatment group, it's obviously not acting as a good counterfactual. So a synthetic control doesn't solve that problem. Also, if there are anticipation effects, so maybe forward-looking economic agents react in advance to the policy intervention, results could be biased because, I mean, they have time to react, so their behavior will change before the actual treatment period. So for comparing the before and after, then it might not be as large as it should be because they're already acting in the pre-period, right? In that case, like same as the difference in differences though, you can try and predate the treatment period to capture anticipation effects. Okay, any questions on synthetic control? I will get to showing you guys how to code on Stata on Wednesday. And that should clear up a lot of questions about choosing your predictor variables as well as the weights. Okay, great. So this paper by Carden-Krueger is a super classic difference in differences paper. We're going to step back. Remember, this unit covered difference in differences and synthetic control. So we're going to look at one of each. So this is a difference in difference paper and it looks at the effect of minimum wages and employment. So a case study of the fast food industry in New Jersey and Pennsylvania. So this is a classic difference in difference where one state receives treatment and they use one state as the control group, which is kind of, after we talked about synthetic control, a little arbitrary which state they chose. Okay. So basically in 1992, this is becoming an old paper already, New Jersey's minimum wage rose from $4.25 to $5.05 per hour. So I saw a decent jump in the minimum wage. And the authors are going to want to estimate the effect of this minimum wage on labor market outcomes, specifically for teenagers. So to evaluate the impact of the law, the authors survey 410 fast food restaurants in New Jersey and then Eastern Pennsylvania before and after the rise in minimum wage. You guys can see how they're going to do before and after for New Jersey, which is the treated group, and then Pennsylvania, which is the control group. So they're using the comparison of employment growth at stores in New Jersey and Pennsylvania to estimate the effect of the higher minimum wage. So based on economic theory, we would think that higher minimum wages will reduce labor demand and therefore reduce employment, right? So if the minimum wage increases, firms are willing to hire less labor because it's more expensive. So we would think that employment would decrease because it's more expensive to hire one more unit of labor, right? So that's what theory says. And Card and Kruger are going to test this using difference in difference analysis. So the treatment group is New Jersey, and they specifically look at fast food restaurants to, check the effect of the minimum wage. So these fast food restaurants experience this treatment effect, so increase in the minimum wage. And why do they focus on restaurants rather than the whole economy? Well, the fast food industry is good because they're largely a minimum wage employer, right? So they hire a lot of workers at minimum wage. So you know that they're going to be affected by this policy, maybe more than other firms that tend to hire more educated or higher earning labor. Also, it's really nice because you know that there's fast food restaurants everywhere. It's going to be pretty standard across states. Whereas if you look at an industry specific employment outcome, maybe there's different industries within different states. So this really guarantees that there's a consistent labor market within fast food industry in both treatment and the control group. Okay, so their control group is then fast food restaurants in Pennsylvania. And then they're specifically going to look at teenagers because it's usually teenagers earning the minimum wages. If you have any college experience, or older people tend to earn higher than minimum wage. So they're just concentrating on a population that would be highly affected by this policy. So obviously that's good for ensuring that you capture the effect of interest, but it might not have external validity for the whole working population, right? Because we're specifically looking at restaurants and we're specifically looking at teenagers. So there might not be much external validity, but it is ensuring that the authors are looking at the population most affected by this program or increase in minimum wage. Okay, so they're obviously doing a difference in difference here, and they're going to compare the change in employment between New Jersey to the change in employment in Pennsylvania. Okay, so let the Y1 ST be fast food employment at restaurant I and period T if there's a high state minimum wage. So that's basically New Jersey after they receive treatment. And then let Y0 ST be the fast food employment at restaurant I at period T if they have a low state minimum wage. So that'll be Pennsylvania. So those are the potential outcomes. And remember that we can only observe one for the treatment or control group. So for example, we see Y1 IST, or it should just be Y1 ST, New Jersey, in November of 1992. So that's after the minimum wage change. Okay. Wait, what? I think I'm missing a slide there. Okay, what? The above formula. There's no above formula. I think we're missing some assumptions, but of course, with a difference in difference, what is our primary assumption? It's the common trends, right? So we need basically our outcome variable to look similar between the treatment group and control group before treatment. So they need to experience the same trends so that we know that our control group can approximate for the time trends that the treatment group would also observe. Okay, so the author's cause and effect question is, what is the effect of a minimum wage increase on employment outcomes? So yeah, as I said, they're choosing fast food industry workers because these workers are mostly affected by the minimum wage policy. And these fast food restaurants largely have to comply with the minimum wage regulations. So they're not going to be in the informal market. They're going to have to comply to minimum wage laws. So we know that the treatment groups are actually receiving treatment, right? So we're going to have full compliance, basically. We're not going to have partial compliance because everyone has to increase their wage to the minimum. Thirdly, the job requirements and products of fast food restaurants are relatively the same. So that makes it easier to obtain reliable measures of employment, wages, and product prices. So we know that they're producing similar products, so it's easier to make the two groups comparable, right? Okay, so the authors construct a sample of fast food restaurants in New Jersey and Eastern Pennsylvania from Burger King, Kentucky Fried Chicken, Wendy's, and Roy Rogers. So the first wave of the survey was conducted by phone in February and March of 1992. And so that's basically the baseline survey, right? So this is pre-treatment. We're gathering data on whatever characteristics we need, as well as the outcome variable. So obviously this must be a prospective analysis since they're conducting baseline information. But obviously it's not random which restaurants experience minimum wages and which ones do not. So they're still going to need to use this difference in differences methodology for causal inference. So they do have the benefit of having baseline data, but unfortunately, I mean, it's not random. So they're going to need to use a different methodology than just using a simple OLS. So this surveys were conducted in two waves. So wave 1 is the baseline, and wave 2 is the post-treatment period. And that would be 8 months after the minimum wage increase. Okay, so there's about 10% of attrition. If you guys remember what the problems of attrition are, it's that it might not be random which people decide to drop out of the study or which groups. So if it's the most unsuccessful businesses, maybe they can't make it past the minimum wage increase. Maybe they lose all of their profits and have to, stop, what's it called, when they have to sell their business. That would maybe overstate. It would definitely bias our true impact. So we need to be considerate about the attrition rate and which groups decide to drop out. Because 10% is pretty high attrition. So this is showing the basically baseline table of characteristics. So you can see the distribution of store types between New Jersey and Pennsylvania. And then this is the t-statistic, right? So we don't want to see it higher than 1.96 on the absolute value. So there's all these different, My household is so loud. I'm sorry, this is distracting. Okay, so you can see that these, they're slightly not too balanced. I guess it's not statistically significant though. So none of these differences are statistically significant because this is the t statistic. So if it were greater than like 1.96 on the absolute value, we would be concerned. But it's not, so we're not concerned about the differences here. Do you guys see any differences in characteristics that you would be concerned about? What do you guys see that's statistically different? Anyone? Oops. Okay. Well, what I see is this full-time employment, FTE employment. So that's the number of employees that work full-time. Price of full meal. Oh yeah, price of full meal too. So these two. So number of workers who have full-time employment and price of full meal. Those are statistically different between the two groups because they're both larger than 1.96, that absolute value. So that could be a bit concerning because this FTE employment is the outcome variable of interest, right? So we want to look at the effect of the minimum wage on how much full-time employment there is between New Jersey and Pennsylvania. So the fact that it's different at baseline to me is really concerning because that's your outcome variable and that's what you want to be the most balanced. But I mean, this paper got published, but it was the 90s, so it wouldn't be published if it got submitted today. And then price of full meal is different as well. Yeah, those are two things. It could be concerning, like if maybe just the cost of producing goods is higher, they won't be able to afford as much labor, or the cost of living might be higher in that area. Okay, and so this is the means in wave 2. So this is the outcome period. So this is the FTE employment, so the number of workers who work full-time on average between New Jersey on the left and Pennsylvania on the right. So this is our main treatment difference. This is our means of difference of means between the treatment and control group in the post period. It's really interesting to me because if you look at the difference in period 1, you see that New Jersey is at 20.4 about on average number of full-time workers, whereas Pennsylvania is at about 23.3. So that's the pre-treatment period. And then you look at the post-treatment period, and you can see that New Jersey actually stays about the same. So it increases from 20.4 on average to 21 full-time workers on average. So that's not much of an increase, but you see that Pennsylvania, the control group, sees a large decrease in the average number of full-time workers. So the problem is that Pennsylvania is supposed to be the control group, right? And so it's supposed to reflect the economic conditions that the treatment group would have observed in the absence of policy. So do you guys really think that New Jersey, if it didn't receive a minimum wage, would have received or would have experienced a huge drop in full-time employment? Or does it just kind of seem random? Like, to me, it doesn't really make sense. So I just want to show you guys. It's too far. So we'll keep that in mind when we go look at the pre-trends table. So This is just explaining the pre-trans table. Okay, so the methodology of the paper is using DS to be a dummy for high minimum wage states. And then, so states is denoted by S, and post T will be a dummy, time dummy equals to 1 if the time period equals 1. So this is basically our standard difference in difference setup that we talked about. So if you receive an increase in your minimum wage, the treatment dummy D will equals 1, so that's for New Jersey, and post will equals 1 if it's after the treatment period. So then, wait. Okay, so then their outcome variable, so YISP, is equal to a state fixed effect or state variable plus a time variable, and then your basically interaction term. So this is your diff and diff coefficient. This, I don't know why this was written as lambda, no, that's gamma S, and lambda T. That's the same as saying DS plus post T, basically. That would be more clear, but that's what they're doing. So that's their difference in difference methodology. And then you can see that you can obtain the first and second differences observed by New Jersey and Pennsylvania. And so there's 2 time periods, 0 and 1. So 0 will be pre-treatment and 1 will be post-treatment. So the expected value of your outcome given state equals Pennsylvania and T equals 1 minus the expected value of the outcome given Pennsylvania and T equals 0. So that's your before and after comparison for the control group. That's just going to be a difference between the time trend for period 1 minus the time trend for period 0, right? Because remember that these two outcomes are also a function of their individual characteristics, but since their individual characteristics are constant over time, they get eliminated through this equation, so we're only left with the time trend, which is exactly what we want to be able to estimate the time trend for our treatment group in the absence of treatment. Okay, and so then we take the same before and after difference, right? After minus before, except our state is New Jersey, which is the treated group. So then we're left with the same time trend plus a treatment effect. So that's plus our delta, which will give us the true treatment effect of interest. So yeah, that's just combining the two, and that's what basically subtracting off the time trends gives you the treatment effect, as we talked about in an earlier class. Okay, and so this is their main outcomes table. So remember that their outcome of interest is the number of full-time employment workers on average for the New Jersey versus Pennsylvania. So you can see that you have the number of full-time employment workers before and then after. So for Pennsylvania, they have 23.33 before, and then it drops down to 21.17 after. And then for New Jersey, the treated group, they start with, on average, 20.44 full-time workers in a fast food restaurant, and it actually increases to 21 after. And so, of course, when we're doing a difference in difference, you take your before and after comparison for the treated group minus the before and after comparison for the control group, right? So they do that in row 3. So you see the change in mean full-time employment, full-time employees employment. I think that's it. And so you go 21.17 minus 23.33 for the control group, and you're left with this number minus 2.16. And you do the same for the treated group, so 21.03 minus 20.44, and you receive the answer of 0.59. And so to do the difference in difference, this is the result. So you go 0.59 minus negative 2.16, right? Because you want to subtract the control group from the treated. So it's treated minus control. And your actual difference in difference effect of interest is 2.76. So we're saying that the minimum wage effect, so an increase in the minimum wage in New Jersey, resulted in an increase in the number of full-time employment workers by about 2.76 workers per fast food chain. What does that result seem to you? So what do you guys think of that? Why, I don't know. Do you guys have any thoughts about the positive estimate? Does it make sense intuitively, or is it opposite from what you expected? So if we're looking at the effect of a minimum wage increase on employment, what would you traditionally expect to see? It is opposite. So Nicholas, that is correct, because if you think about the effect of a minimum wage on employer choices, employers will typically choose to hire less workers. So we would expect to see less full-time employment. Yeah, negative effect, Susanna, same thing. So we would expect to see a negative effect, and that's what other papers have traditionally shown, that typically labor demand is very elastic. So when there's an increase in minimum wage, we would expect employment to go down. But this result is showing the exact opposite, that when you increase minimum wage, full-time employment hours actually increase. So it's really opposite to what theory predicts. And now it's a question of whether this result is true or whether it's just random luck and maybe there was an error with the assumptions. So to know that, we should look at the common trends. Okay, no, they haven't shown, we're about to look at them. We're going to look at the pre-period trends. When they originally posted this paper, they did not show the pre-trends. And then later on, like 5 years later, they did show it. And then this paper just was like down the garbage because their trends did not satisfy. Okay, so here's the common trends. Oops. So notice, so this is kind of confusing. This is like way older data, but this is really the part we're interested in. So remember that wave one was, that's a nope. That is a nope. Wave one was conducted in January, I think it was 92, right? So that was their baseline period. And wave two was the second line here, like 8 months later. So this is when they conduct their baseline data. And so this is basically their pre-trends. And so the treatment occurred somewhere, I can't remember what day. Do you guys remember what year I said they received treatment? So treatment occurs somewhere in between these two lines. So we're going to consider this as our pre-treatment period. And so New Jersey is this flat line. And then these two lines are the Pennsylvania. So they're only including the 7 counties, I think, is what they said. So it's this large spike. I mean, it's really small, but do you guys think that common trends are satisfied just looking at this pre-trend period? I mean, I think obviously not. Yeah, no, because clearly, I mean, they just don't trend the same at all. They're both pretty cyclical, like the employment, but you can see a huge spike in the employment, full-time employment for Pennsylvania, and then it just decreases after that. So it really seems like they got lucky, or not lucky, but they had an error in their estimation because they collected data from Pennsylvania when they were at a relatively high point in full-time employment, and then they just see a gradual decrease over time. Whereas, I mean, it's hard to say what the true trend of New Jersey is, but I mean, any modern paper based on the pre-trends, the paper wouldn't be published. So it definitely got invalidated that way. So I definitely wouldn't trust these results at all. Okay. So based on that, obviously I would say maybe they should go back and try a synthetic control, since they're only the Pennsylvania as a control group doesn't offer a good comparison. But I mean, well, CARD's dead now, I think. And I mean, it's really old paper, so they haven't gone back, but there has been new papers that have looked at the effect of minimum wage and have used different methodologies. So this one by Dube et al. 2010, I think it's Dube actually. They look at the minimum wage effects across state borders, but they use a different methodology. There's a recent one. Yeah, I think there is too. So this one, they're looking at basically states that have variation in the minimum wage, but they only look at basically counties or districts right beside the border. So and they do that all across the United States. So they actually combine about 1,000 different differences between really close together areas. So they definitely find different results than what Card and Kruger did. We're definitely not going to get to this paper today because class is over now. And on Wednesday, I would like to get to the following paper, which is in this chapter 5 on synthetic controls. So I might not present this paper to class. So if you do want to learn a better methodology on how to estimate the minimum wage effect, then definitely check this paper out right here. Okay, so on Wednesday, we will be looking at some STATA work just to examine a difference in difference and synthetic control, and that should prepare you guys for your last assignment. And within this week, hopefully I'll get you back your assignment 2 grades. Okay, if there's no questions, I'll let you guys go now. Okay, great. Have a good night, you guys. I'll see you all on Wednesday. Bye. Ciao, ciao.